Hello AP Calculus and welcome to the day flip video. So my period A class right now, it is Thursday. We got homework, bookwork tomorrow. And period G class, you guys are on Wednesday and you got bookwork for the next couple of days. Okay? Please stay on top of this material, guys. Alright? Try to work together and help each other answer questions so that right when we come back from vacay, we can just get right into AP exam review. I want to use as much time as possible to make sure you guys are ready for this thing, okay? So this is day 2 of 7.3, and we're going to start with clarifying the washer method a little more, okay? We're going to go through some examples of washer-specific method, all right? So first off, we've got this problem right here. It says the region in the first quadrant enclosed by the y-axis and the graph of cosine x and sine x is revolved around the x-axis to form a solid. Find its volume. So this right here is a picture of an example. So this right here was the original region, this little piece right here. Okay? Then if I flip this thing across the x-axis, it's right down here. Okay? This little region down here. So the region in the middle, this triangular region right here, is blank, is no accumulated area. That's the big indication, guys, that it's a washer, okay? So again, washer, the difference is it has 2 radii, factor out a pi, and then you're ready to go, all right? So, you know, the book already solved the problem for you, 0 to pi over 4, pi, you know, pulled out, cosine squared x minus sine squared x. This right here, guys, is big R and little r, and then they pulled the pi out, and then cosine squared x minus sine squared x. They simplified to cosine 2x using the identity, and then they simplified and got pi over 2. All right. So just another example of the washer. Let's take a look at this problem. This problem looks just wonderful. Find the volume of solid formed by do not close. Thank you. Find the volume of solid formed by revolving the region bound by the graphs of root x and x squared about the y-axis. It's shown in figure 7.2. I love this actually. It looks like kind of a flower pod. We use this problem all the time, root x and x squared. It's great. They intersect at 1, 1, and we're going from 0 to 1, 0 to 1, x and y, which is super awesome because you can't get your bounds mixed up because it's just 0 to 1, 0 to 1. Okay? So right here, the book gives us a nice example of exactly what we're working with here. This right here was the original region. Okay? And this right here is the region that's reflected. All right, and as you can see, all this area right in the middle here is open space. There is no actual area accumulation. That highlighted region is empty. Okay, so we know for a fact that this example is going to be a washer. All right, here, right, there's the right here. I don't know what I'm saying, but right here, this line, the x-axis, is the rotation axis, okay? What you would do is, since we're rotating this thing across a horizontal line, you'd slice this thing vertically, okay? So you begin at the origin, not the origin, but the original, axis of rotation, the start of the problem right here. You're going to go until you bump the curve. Remember, don't use the image. Don't use the reflection. You only use the original, okay? Right until you bump the curve, that distance is little r. Okay, so right there to down here, that's little r. Okay? Obviously, you know it's this curve. This is the curve x squared, so little r is x squared. Then, from the actual start of the problem, the axis of rotation, to the end of the problem, right here, that is big R. From here down to here. Okay, and big R is given by the curve root x. Let's enlarge our picture. So here we go. Washer. Thickness. I know my thickness is just awful, just terrible, but it's important to have actually because it represents the dx or the dy. That's why we can integrate. Okay, so my little thickness right here, it's terrible. You got to draw it. So let's go ahead and put some stuff in our diagram. So you got little r. You got big R. Now we just said little r is x squared, big R is root x. We're ready to solve the problem. Area of one of these bad boys is the area of the circle, big outside circle, minus, so we'll just put it right here, minus the little inside circle. And as we said in video 1, pull out the pi, subtract the radii squares. And then insert our data. Root x squared is x. X squared is x to the 4th. This right here represents the area. That's the hard part of the problem. The easy part is finding the volume. Volume's the integral. Now, like I said in the beginning, it's nice. You can't really mix up the bounds because it's 0 to 1 in both the x and the y direction. So you slap on pi x minus x to the 4th dx. Feel free to pull that pi out. Oh, that was just atrocious. Let's try that again. 0 to 1, x minus x to the 4th dx. Use some parentheses if you need to. Again, this is just a simple integral problem, but just to simplify the process, simplify the length of the video, you get 3 pi over 10. Okay? And that represents the volume of the region. So let's take the same figure and do the same thing, but this time about the y-axis. Okay? So let's draw a picture, because the textbook didn't give us one in this problem. So here we go. So here's my original drawing. It's 0.11. What I'm going to do is rotate this thing about the y-axis. So I always like to use dashed lines. Okay, this right here, negative 1, 1. And here we go. Disc or washer? Well, first off, let's slice this thing. Boom. We had a vertical axis of rotation. We sliced this thing horizontally. Again, I can highlight it if I need to, but here it is. All this is wasted space, okay? This has to be a washer. There's no accumulation of any area there, all right? It's definitely, without a doubt, a washer. Start from the axis of rotation. Only use the original. Don't use the reflection, and go until you bump your curve. That little distance is little r. Right there, okay? From the axis of rotation all the way to the end of the curve, that's big R. Alright? So clearly a washer. Let's enlarge our diagram here. We'll use this. We'll use a washer and a little thickness. Hey, that's not bad. We got little r, we got big R. Let's figure out which one's which. In this particular problem, it looks like little r is going to be the square, but it's got to be y squared, and big R has got to be root y, okay, because I had to go back and change the actual curve right here, y equals x squared, and y equals root x. I had to change them into x equals form. Y has to be my variable, okay? Now that that's ready, I'm ready. Volume equals, oh, jumping the gun, not that ready. Area equals pi times the squares of the radii being subtracted. That's y minus y to the 4th, okay? Y minus y to the 4th, and now I'm ready. That's the hard part. The easy part is just integrating. So let's pull my pi out. I've got 0 to 1. I've got y minus y to the 4th dy, and I get the same region, or excuse me, the same volume, which isn't a coincidence, right? It's basically the same exact accumulation of area because it's from 0 to 1 on both sides. All right? That's a couple of good examples of the washer method a little bit further. So it doesn't really matter if you're doing a horizontal or vertical. You can have a disc or a washer in both scenarios. It just depends on the curve. It depends on the region. Okay? All right, let's do an AP problem. Here we go. I'm going to leave this up. The notes are already online. If you want to pull the notes up so you can look at the problem too, because unfortunately I'm going to have to push this down so I can write. But if you want to pause the video and write this down in your notes, that would be a good strategy too. But let's go ahead and get started. It says R is the region, the shaded region, the first quadrant enclosed by the graphs of e to the negative x squared and 1 minus cosine x. In the y-axis shown below, blah, blah. Okay, so there's R, there it is. AP always labels the regions. So if they have multiple regions, they'll call them like R and S, stuff like that. All right? So let's see. Find the area of the region R. If they ask you to find the area, that's asking you a 7.2 question. Okay, so we're just simply finding the area. So let's go ahead and see if we could do that. Well, looking at the picture, it looks like I've got two curves, right here and right here. So would it make sense to do a vertical rectangle or would it make sense to do a horizontal rectangle? Well, clearly a vertical. one, all my functions are in terms of x, right? X is the variable. And two, there's always a top and there's always a bottom. I don't have to ever split the region up. So to solve part A, I think I'm going to use a vertical rectangle. And that means that everything needs to be in terms of x. Okay? That's just my laundry buzzer. Don't worry about it. So I think we're ready. The only thing I don't know, though, is the intersection points, because I have to know the intersection points. If I go back to the picture, I have to know these points right here to be able to integrate, because I know this one's 0. It's snug up against that. So I know this is going to be integral from 0 to blank, and I got to figure out what that is. So let's figure it out. So what you need to do is set the curves equal to one another. What I would do now is go to the graphing calculator and figure out when these curves intersect. And after doing that, I get this thing right here. So for those of you saying, hey, it's 1. No, it's not actually. You have to solve it algebraically because it's 0.941944. And even more importantly, do not round that number. Not even 3 decimal places, okay? Don't round it until the end of the problem. So I think we're ready. So volume equals the integral from 0 to that thing right there. What I'm going to do is call that thing S for Schachter. Just so I don't have to keep rewriting it. So this is an S. It stands for point. No, I don't know. I'm actually not even going to do that because it's probably going to confuse someone. We'll just write it. We'll write it. 0.941944. I don't want people to think it's a 5 or anything. We'll just write it. Whatever. It's all good. Top function minus bottom function. Okay? And plug that into a calculator, you get 0.591, which is the answer to part A. Alright? Part B. Find the volume of a solid generated when the region R is revolved about the x-axis. Okay. Right off the bat, check this out. Look at this. Right? It's a little thicker than I want it to be. Sorry, because just I can't really adjust that. Oh, yes, I can. See that? Look at that. Learn something new every day. That can really get in there. All this is wasted space. If I flip R about the x-axis, all this highlighted stuff is not being is no volume, no area. So it's a washer. Okay? Part B, if I revolve R about the x-axis, it's a washer. Hey, what do you think about revolving R about the y-axis? Right? See how it's snug up against? There's no actual area there. What do you think? Disc or washer? No one's going to answer? Really? Anyway, I'm just kidding. Yeah. So if you rotated R about the y-axis, it's actually going to be a disc because it's all snug up against that. You're not going to have that accumulation that's being wasted. So it'll just be a nice solid region. So my humor aside, let's go solve B. So we know we're going to have a washer. Okay. Actually, again, I can't really scroll down to find the picture there. But if I were to find this thing and I wanted to do a washer, I'm rotating about the x-axis, right? It's a horizontal axis, so that means I slice this thing like this, vertically. And if I wanted to, I could draw my region. You know, R would just be like down here. So, you know, if I wanted to, it could go like this. Something like that. Kind of like, it's hard to do with dashed lines, but I probably shouldn't have tried. It's pretty bad, but this would be like R's reflection. Alright, so let's get my radii here. Here's little r. Okay. Here's big R. Okay. So from the axis of rotation to you first hit the curve, from the axis of rotation to when you end. Alright? So I think that's everything we need. So, I mean, let's just look at it real quick. It looks like little r is going to be the 1 minus cosine x. And the big R is going to be this guy right here, which is the e to the negative x squared. I think we're ready. So let's go down and just do part B. And we know we're going to have a washer. And there's my thickness. Here's little r. Here's big R. Little r we just said was the trig. And big R is e to the negative x squared. I think we're ready. Figure out the area of this thing. Let's see. So the area of this thing right here is going to be pi factored out. Big R squared minus little r squared. Which is going to be Looking up at the top, minus this thing squared, dx. I should probably drop another parenthesis right there. Okay, oh, jumping the gun with the dx. Sorry, still finding just area, not integrating yet. All right, so that right there, this whole string is the area of my slice that I've just created. So that's the hard part, easy part. Volume, pi, integral, my bounds. I sliced vertically. I use x. Luckily for us, we already figured out the intersection point. And then I post this whole thing in there. Okay, and what I would do now, because your AP problems are going to look just like this, pause the video, go try to find the number. Okay, pause it, go solve this. Inputting things into your calculator is extraordinarily important. Should get 1.747. Alright, that's the volume for part B. Part C. The region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a square. Find the volume of this solid. Well, this shouldn't be too bad. It says that each cross-section is a square. Okay? Well, how do you find the area of a square? It's just side length squared, right? Now what I have to do is find the volume. So what I need to do is see if I can figure out, let's clean up my diagram a little bit. What I need to do is figure out, well, I actually don't need too much, because I know I can figure out the actual side length of one of these cross sections. And if I were to just put my rectangle right inside, anywhere, right there, the side length, again, now this is going to be a square because they told me. So if these side lengths are equal, if I fit this in, then it's just going to be top minus bottom again. It's just going to be like part A when I'm finding area. So I know that top minus bottom is going to be the length of the side of the square. So I think that's all I would need to start the problem. I already have the intersection point, and I know that the area of a square is simply s squared, which is simply going to be the top minus the bottom. And I already worked with this. This is e to the negative x squared minus 1 minus cosine x. Okay? So I just have to basically sum these up. I know that this is the area of my squares, and I know that I'm going from 0 to 0.941944, and I just integrate all my squares. Alright, because the squares change depending on the value of x. Throw on a dx there, and this right here is going to be the answer to part C. Okay, so if I can extend the page, the volume is going to equal, pause the video, go try to find that number yourself. It's going to be 0.461. Alright, so that time, instead of working with a disc or a washer, I was working with a square. So it's relatively the same thing. I just had to figure out the area of my square, and I used 7.2 top minus bottom, and I figured out that one side length of the square is going to be this thing right here. And actually, thinking about it right now, side length squared, I actually should have squared all of this. This is just one of the side lengths. So that's my bad. The answer's still right. The work just needs that. Alright? Side length squared. So that's now perfect. Sorry about that. Answer would still be right. Okay? Alright. We'll skip that because I give it to you on the AP exam. So, known cross sections. This is like the last thing in this section. It's a little bit different from anything we've been working with. Basically, a lot of times in the disc and washer problems, it's not known what figure you're working with, right? Known cross section is basically the name for part C, what we just did. When they tell you exactly what the cross section is, they told you it's a square. Alright? So, a lot of times in these figures, they tell you exactly what the cross section is. The cross sections are squares with base in the xy plane. If you kind of ask yourself the question, this right here, the base is the circle, x squared plus y squared equals 1. Alright? And you kind of ask yourself the question, where exactly do these cross sections exist between? Well, if you split the semicircle up into the top half and the bottom half, the positive half and the negative half of the radical, because we're going to isolate y, we can simply conclude that these cross-sections exist between these two semicircles. And these two semicircle equations are negative root 1 minus x squared and positive root 1 minus x squared. And that's just taking this equation right here and solving it for y. Okay? So now the idea is, if they exist between negative root 1 minus x squared and root 1 minus x squared, how could you find like the width of one of these cross sections? And that's just 7.2. In this particular example, to find the width of it, you're just going to do like top of the curve, the positive, minus bottom, the negative. So let's see what that looks like algebraically. If you wanted to find the width of one of these cross sections, all you got to do is you got to just do the top minus the bottom, like we just did in part C of the other problem. That's going to be root 1 minus x squared minus negative root 1 minus x squared, which is plus plus, which is 2 root 1 minus x squared. And this, guys, represents the width of one of the cross sections. So you may ask yourself, well, if that's the width, or in essence, one of the side lengths of one of the cross sections, well, what's the area of one of the cross sections? Well, it was given that the area, or that these particular shapes are squares. The area of a square is simply side squared, right? Which we were calling it all along the width. So that's just the width squared. And if you square 2 rad 1 minus x squared, you get 4 times 1 minus x squared, because the rad goes away. And this right here would be the area of the cross section that was provided to us in the above picture. Okay? So the only thing that changes here is we're just being told exactly what figure we're working with. Alright? It doesn't have to be a circle or a circle with a hole in the middle anymore. It could be anything. It could be anything like equilateral triangles. You guys know the formula for the area of equilateral triangle? You got to memorize that bad boy. Root 3 over 4 side length squared. Okay? Got to know that. So let's look at the problem. Equilateral triangles. Once again, this circle, x squared plus y squared equals 1. This circle is split up into two parts, the positive part and the negative part. So these cross sections, even though that they're triangles now, still exist between root 1 minus x squared, we'll do the negative first since it's the smaller, and root 1 minus x squared, right? And these are all y equals, of course. Okay, so they exist between those two values. So suppose I asked you how to find the area of these equilateral triangles, okay? So if you want to find the area of the equilateral triangles, again, you're going to basically have to use the area formula. It's root 3 over 4 side length squared. Well, what in the world is this? How do you find the side length? Well, it's pretty easy. We just did it in the last problem. Side length equals the top, which was the positive, minus the bottom, which is the negative, which simplifies neatly to 2 root 1 minus x squared. That's s. Okay? So now if I ask you what the area was, well, you just insert s. So let's go back, and area equals root 3 over 4 side length squared. And this simplifies, like the last problem, to root 3 over 4. And this is going to be times the 4. I guess I could have just simplified that. This 4 is going to go away with the 4 that I'm about to write, or would have written had I not simplified. 1 minus x squared. Okay? That's the area of one of these equilateral triangle cross sections. So now suppose I asked you volume. Well, you'd integrate from whatever to whatever of that dx, and that could give you the actual answer. Okay? So let's look at one more. This is the last one we'll look at. This time we'll do the semicircles, right? These are just the 3 pictures from like day 1 slides, so they should look familiar. So suppose this time it gave you y equals 2 sine x. And I believe we already looked at the work up to this point. Actually, you may have even looked at the answer. I don't quite remember, but let's just kind of re-look at it. So let's see. It says that the radius is 2 sine x over 2, which is just sine x, because the 2's cancel. So the area is, it's a semicircle, so you have to divide pi r squared by 2. And we're going to integrate that from 0 to pi. We're using 0 to pi because we're using the x values. And just sine squared. And then you plug that in a calculator, and out came 2.47 cubic inches. Okay, so that's just another example of a known cross-section, which doesn't necessarily have to be a a circle or a circle with a hole in the middle. It could be anything, but the difference between this is that they're actually telling you exactly what that known cross-section is. Okay, so that's it for notes. At this particular time, what I'd probably do is tell you guys, all right, does anyone have any questions? And then we'll start working on some more practice problems. So that's it for day 2, but I'm going to also put another video up because I'm going to give you guys a worksheet to try some of these. All right, and I'm going to put another video up of me doing a couple of the problems from the worksheet so you guys can get some feedback and some answers before you try the rest of them, obviously. Okay? So today your homework is to go and finish the bookwork. So obviously I'm giving you all of class tomorrow, but the best thing to do would probably be to start it yourself tonight. Go home, start the bookwork. If you're getting some things, awesome, do those. And if some things aren't making sense, that's what you want to bring to class tomorrow, work in groups and ask those questions. Okay? So work on that and look forward to the next video with the worksheet.